All right, let's take a look at PBKDF2. This is a real important component of cryptography as it's normally used, where you don't have a random key. Instead, you start from a password. And so you hash passwords with hash functions to make it hard for criminals who steal the hashed passwords to recover the original passwords. And another use for the same procedure is to derive cryptographic keys from passwords. So this is password-based key derivation function. And this is a weak spot in modern cryptography. There's this, and there's another system called bcrypt and another called scrypt that all do pretty much the same thing. But none of them are really ready for enterprise prime time with all the necessary requirements in all the use cases being covered. So people are arguing about it quite a bit. But anyway, here's what PBKDF2 does. You give it a pseudo-random function, a password, and a salt, and then it encrypts with a certain number of iterations and gives you an output of whatever length you like. And so there's a function that will do it for you here. And you can encrypt, for example, this is going to use MD5, an old hashing system, and encrypt the word apple with one iteration and give me 16 bytes of output. And it gives you a random 16 bytes key. And this is what happens when you, for example, go to an iPhone and you type in a password to log into your iPhone or a PIN. It takes that and it runs it through this kind of hashing value to turn it into a key of appropriate length to encrypt things. iPhones have about 5 or 6 layers of encryption with AES. There's a key that is used when you first power it on, another one when you log in, other ones for different purposes. Each stage of the boot up process is encrypted differently. And on it goes. So you can calculate a hash this way, and then you can worry about type conversions. And so the whole point of PBKDF2 is to use it with AES and decrypt something like a hard drive. So you have the user enters a password, which is used to derive a key, and then used to encrypt data. So here I've got clear text, and I'm going to encrypt it with the password Apple. So I take Apple, turn it into a key, and then use it to encrypt this. This is how it's actually done. So users don't have to remember those ridiculous 16-byte random keys. All right. And so that's fine. And I've got some challenges where you perform this operation using various things to derive keys from passwords and then decrypt things. And here you begin cracking things. The password contains 3 lowercase letters, and that's all you know. So you're going to have to try all of them. And one thing a student pointed out to me is that you can encrypt virtual machines, and they encrypt the virtual hard drive, and they do it with a very strong system. It turns out that VMware encrypts hard drives with SHA-1, 10,000 iterations, AES electronic codebook, and a key size of 256 bits. So that's up in the range of like military standard encryption these days. And it creates a thing called the key safe, which is a data structure that includes an encrypted key. This is how it's done with layers of encryption. You use the password to decrypt the safe, and in the safe is another AES key that's used to encrypt the data. And so you can take the actual key safe from the VMware configuration, and you can extract the hexadecimal encrypted data from it, and you can get it out as long as you guess the right password. So I've got examples here where you crack a safe, and I made 1,000 possible keys from 0000 through 999. And you can try them. And here's a harder safe, which a student made for me. The first 2 letters are WE, and that's it. And I actually gave them the first 2 and last 2 characters to make it easier. But you can crack these things if you have that kind of information. And it's an important process to see how passwords are used in practice. All right, let me stop this one.